So we might be asked to calculate the area between two curves in a situation where the curve that's the top curve might not always be the top curve. Notice the curve I'm tracing right now is the top curve here for the region S1, but then once we get to the region S2, it's now the bottom function, and then it changes back afterwards. And the quick, compact way of writing that phenomenon is to say that the area between the curves y equals f of x and y equals g of x, between x equals a and x equals b, where we're not saying anything about the relationship between f and g, is going to be the integral from a to b of absolute value of f of x minus g of x dx. Now that formula is great, but it doesn't really help us do the actual calculations. We still need to figure out at what point does f and g switch from being top function to bottom function and vice versa. Okay? So we need to think of it more in that way when we're actually doing a calculation. We're not going to actually use these absolute value bars when we do the calculation. We have to look at the graphs and analyze what's happening and go from there. All right, so in this next example, on that note, we're going to calculate the area of the region bounded by the curves y equals sine x, y equals cosine x, x equals 0, and x equals pi over 3. Now, because these are trig functions, I'm going to think of my tick marks on the x-axis as being multiples of, let's say, pi over 6, just to be on the safe side. So actually, just so I can see the graph even better, maybe I'll put every other tick mark as pi over 6 so we can really see and we don't have to do the zooming in thing anymore. So this will be pi over 6 and this will be pi over 3, and let's just go from there. So pi over 6 is pi over 6, and then 2 pi over 6 is pi over 3, and then 3 pi over 6, which would be this, would be pi over 2. And that's a good place to stop our drawing, because we should be able to graph sine x and cosine x from at least from 0 to pi over 2. So let's remind ourselves. Y equals sine of x. And then actually, let me make one up here and -1 down here. Let's see. So then y equals sine x will have this shape. We know that sine of pi over 2 is 1. Sine of pi over 6 is 1/2. And then sine of pi over 3 is root 3 over 2, which is about maybe there. Remember, we only need up to pi over 3 anyway. Now for my graph of cosine, well, cosine, if we start from 0, it's the y value is 1, and then the next y value would be root 3 over 2, and then pi over 3, cosine of pi over 3 is 1/2. So, and then cosine of pi over 2 is 0, which means we get something like this. And they're asking us to calculate the area of the region bounded by sine x, cosine x, and these two vertical lines. Now, I'm not going to zoom in this time because I think our picture is big enough, but notice we're being asked to calculate this region that I'm shading in yellow. And so you might notice that there's a place where the roles of cosine and sine are switched. From 0 to some number I have to figure out, cosine of x is the top function and sine x is the bottom function. And then after that, sine is the top function, cosine is the bottom function. So the key thing is, what is this number? Well, we have to think about the values of sine x and cosine x. Let's just say between 0 and pi over 2. For which x value are we going to get the same result for sine x and cosine x? The answer is pi over 4. And I know my graph isn't perfect, but this is why we have to do things like algebra and solving equations, because if we draw it by hand, it might not be perfect, and so we might not know exactly what that intersection point is where the role of cosine and sine change. Okay, so what does this mean? Using the fancy formula, we would say integral from 0 to pi over 3 of absolute value of sine x minus cosine x dx. But as I said, this formula is not useful. We're going to focus more on the work we did over here to figure out when is which function the top and the bottom function and where does it change. So to make this more practical, I'm going to split this up into two integrals. Integral from 0 to pi over 4, because that's where the change happens, plus integral from from pi over 4 to pi over 3. All right, in the first integral here, the top function's cosine, bottom function's sine. So let's write that. And we can't forget our dx, because that reminds us of what we are integrating with respect to. And I know it doesn't seem to matter much now, but a lot of you eventually will have to take Calc 3. And even in Calc 2, when you're doing more complicated substitutions and other integration techniques, it's really important to keep track of your dx's. So let's see, what about the second integral? It'll be something dx, the difference of two functions. And in that part from pi over 4 to pi over 3, we have to do sine x minus cosine x, because in that part, sine x is the top function and cosine is the bottom function. Okay, let's go on and calculate these. Antiderivative of cosine is sine x, and then antiderivative of minus sine x would be plus cosine x. And we're evaluating this from 0 to pi over 4. That's just the first integral. The second integral, antiderivative of sine x is negative cosine x, minus antiderivative of cosine x is sine x. And we're evaluating from pi over 4 to pi over 3. And when we plug in these values, again, that's using the fundamental theorem of calculus on the first integral. And then the second integral, when we plug in the numbers to finish out using fundamental theorem of calculus, we have negative cosine pi over 3 minus sine pi over 3 minus the quantity of two things that both have negative signs in front of them. So why don't we just change it all to plus, make it simple. Plus cosine pi over 4 plus sine pi over 4. All right. Take a moment to calculate this and see if you agree after unpausing with what I got. And this would be one way to simplify it. 2 root 2 minus 3 over 2 minus root 3 over 2.